All right, I'm going to finish up here the static and dynamic analysis of this mechanism that we started on Tuesday, because on Thursday, as you know, we're going to work on the ancillary material. Okay, so when I say finish up, I'm going to start over for the sake of completeness, and I'm going to go from the beginning to until the end in this video, and hopefully that will give you the opportunity to go back and listen to the parts that you might have missed in class. Okay, sorry about that. So I just copied these numbers from the board, and I'm going to start by drawing the free body diagrams. Okay, so first thing you do when you do dynamics or try to write the Newton-Euler equations, you draw the free body diagrams on each rigid body. Okay, so what we have here is the first link. Let's work on the first link. It looks something like that. Sorry for the poor drawing. Let me try to do it again. I know it doesn't look as bad as the last one, I guess. Okay, so we have point O right here, point A right there, and the center of mass in the middle, or at the center of this link. Okay, what are the forces that we have, forces and torques that are acting on this rigid body? We have the reaction force from the world or the zeroth frame, a zeroth rigid body to the first rigid body. So I'm going to call that F01. In class, I call this FR for reaction force, but let's just call it F01, okay? Because the force is coming from the zeroth frame, zeroth rigid body, which is the world, to the first rigid body, which is this particular link we're talking about. Then there is a reaction force that comes from the second rigid body to the first rigid body, and it acts at point A. And remember, we call it F21. There is a gravitational force that acts at the center of mass, and that's M1 times G. And let me make this G, put a arrow on top of this G to make sure that this is the actual gravitational acceleration vector, not just the scalar 9.81. Okay. There is a motor torque that is being applied, and I'm going to draw that over here as tau 1. And if you recall, tau 1 is in the z direction, the common z direction of the frame. So I'm just going to say this is T1 in the z0 direction. Okay, so these are all the forces and torques on this rigid body. But we also have inertial forces and torques, right? Inertial force would be in some direction that we don't know. It's going to come out. It's M1 times acceleration in the zeroth frame of the center of mass. Yeah. And then the inertial torque or inertial moment acts about the center of mass. That acts about the center of mass was what? Minus the moment of inertia of the first rigid body times the angular acceleration of the first rigid body minus angular velocity of the first rigid body the moment of inertia of the first rigid body times the angular velocity of the first rigid body. Okay. Sorry about this clutter. Let me try to be clinical and move it right there. There we go. Okay, so we said that for systems that move in a plane or in parallel planes, remember that this term right here, this one, omega cross I omega, is always in the direction that's perpendicular to the z direction, and so this thing, we can set that to 0 and only consider this one as the inertial torque. And Again, I repeat that you can do this only for systems that move in a particular plane or in parallel planes, but those planes have to be parallel to each other, so you can assume that they move in the same plane for analysis purposes. Okay? So these are all the forces and torques on the first rigid body. On the second rigid body, let me move this a bit further down. Something like that. We do the same, we go through the same exercise. So first draw the second rigid body, something like that. This is point A, this is point B, this is point C2. Of course, the force due to gravitation or gravitational force acts at the center of mass. It's m2 times g. The force that the reaction force from the first rigid body to the second rigid body acts at point A. And then there's a torque, tau, 2, that acts on this rigid body by a motor that is placed at point A, right? Okay, and these are the external forces or in torques, but there's also, of course, the inertial forces and torques as there is on the first rigid, there was in the first rigid body. And the inertial force, of course, again, is in some direction that I don't know, so I'm just arbitrarily drawing the direction. It is minus m2 times acceleration of the point C2 in the zeroth frame. Yeah? And the inertial torque acts about the center of mass, again, is minus the moment of inertia of the second rigid body times angular acceleration of the second rigid body minus the angular velocity of the second rigid body. Every quantity I'm talking about here is with respect to the zeroth frame, right? Cross moment of inertia of the second rigid body times angular velocity of the second rigid body. Again, because of the planar motion assumption, I can set this last term to 0. Okay? Very good. Now, and these are all the forces and torques on the second rigid body. Now, I'm going to write the Newton-Euler equations for the first rigid body and the second rigid body, right? So, the force balance on the first rigid body tells me I need to have F01 plus M1G minus F12. Why? Because this minus F12 is equal to what? F21. It's equal and opposite due to Newton's third law, right? When you have a when something exerts some rigid body exerts a force on another rigid body, that other rigid body exerts the equal and opposite force on that primary rigid body. Yeah, and that's where this term comes from. So let me continue. And the only force that is left that I haven't written yet is the inertial force, right? This is minus m1 acceleration of point c1 about in the zeroth frame equals 0. That's the force balance. The moment balance about the center of mass looks like, so I need to draw the position vector from C1 to O cross what? F01. That's the moment of the force that acts at point O about the center of mass, plus position vector that goes from C1 to A cross F1 to, of course, that's F21, so I need a minus here. This is the moment of the force F21 about the center of mass. Yeah. What else do I have? Well, I have the torque that I am applying by my motor, right? Plus tau 1 in the z-naught direction. And we said depending on the direction that that this torque is applied, this could be written as minus, but let's just stick to plus, okay? All right, very good. And What else do we have? We have the inertial torque, which is the moment of inertia of the first rigid body times the angular acceleration of the first rigid body in the zeroth frame equals 0. Yeah. And that's it, pretty much. This is for the first. These equations are for the first rigid body. And so let me. I can't get it accurate enough. Let me just try this. Okay. I'm just trying to move these in such a way that I can number them. So let's number this, the first equation. Let's call it the ith equation. This is the second equation. Okay. The third equation is going to be the force balance for the second rigid body. Okay. The force balance for the second rigid body reads what? F12 plus m2 times the gravitational acceleration vector minus m2 times acceleration of the point c1, yeah, equals 0. And finally, the fourth equation is the moment balance equation for the second rigid body. That reads position vector that goes from C2 to A cross F12. Yeah, that's the moment that the force F12 exerts about the center of mass of the second link. Yes. I have the torque that I'm applying with my motor, tau 2 in the z0 direction. And then minus moment of inertia of the second rigid body times angular acceleration of the second rigid body equals 0. Yeah? Very good. And so these are my equations from 1 through 4 in the Roman numbers. Yeah? And we went ahead and started to express these vector equations that right now doesn't have any coordinate system. We started to express these vector equations in a particular coordinate system, and we chose to express it in the x0, y0, and z0 frame. And I repeat what I said in class, which was that since these equations are not tied to any particular coordinate system, you can go ahead and express it in any coordinate system, okay? And they will hold true. They will still give you the correct equations whose solution will give you the acceleration of each of the rigid bodies, okay? Remember that, again, I forgot to write the question here. Well, talk about the question here. I wrote it, but I forgot to talk about it. I am giving you the torques at a particular moment in time, and I'm asking you if the torques are given by these numbers, right? What are the angular accelerations of each of the rigid bodies? In other words, what is theta 1 dot and what is theta 2, what is theta 1 double dot and what is theta 2 double dot, right? That's the question. Okay. And let's keep on going. Okay. So to start with, we don't know what is going on with F01 and F12. So I'm just going to assume that they have components F01, F01X, F01Y, and 0 in the zeroth frame. This is written in the zeroth frame, yeah? And F12 similarly has components F12X and F12Y in the zeroth frame. Okay, again, this is written in the zeroth frame. Okay? So next I'm going to work on, and the other unknowns are of course theta 1 double dot and theta 2 double dot. So since those are the unknowns, I'm going to work on expressing the acceleration of C1 in terms of A1, theta 1 double dot and theta 2 double dot, and similarly acceleration of the point C2 in terms of theta 1 double dot and theta 2 double dot. Okay, I had made a mistake here. I corrected that. It read acceleration of C1 in 0. It should have read acceleration of C2 in 0. Of course, this is for the second rigid body, so it must be the acceleration of the center of mass of that rigid body. Okay. So to do this, of course, so to find the to find the acceleration of the point C1 in the zeroth frame, what do I have to do? I have to take the derivative in the zeroth frame of the velocity of that same point in the first frame. Well, to find the velocity of the point C1 in the zeroth frame, I need to take the derivative of a position vector, right? That goes from a point that's fixed in the zeroth frame, let's call it the point O, to C1, right? So of course, the question then is, what is R O C1 in terms of those thetas? Well, I'll leave that for you to convince yourself, or watch the other videos and find out that this vector is equal to A1 over 2 and sine of theta 1 and minus cosine of theta 1 and 0 in the zeroth frame. This is a vector in the zeroth frame. Okay? So, since this is a vector in the zeroth frame, I can just go ahead and differentiate in the zeroth frame by just differentiating these components, right? So what that means is that the velocity of the point C1 in the zeroth frame is going to read A1 over 2 theta 1 dot cosine of theta 1, sine of theta 1, and 0. Yeah? I just differentiated the components as sine of theta 1 and minus cosine of theta 1. So if I need to express acceleration of C1 in the zeroth frame now, that's another derivative of the components of this vector, because that vector is also expressed in the zeroth frame, you see. So I would get A1 over 2 theta 1 double dot cosine of theta 1, sine of theta 1, and 0, plus A1 over 2 theta 1 dot squared minus sine of theta 1 and cosine of theta 1 and 0. Here, what went on is the product rule, right? There is a product of this theta 1 dot with cosine of theta 1 and sine of theta 1. So if I want to differentiate that vector, I need to use the product rule, which means that I need to differentiate this thing first and write this as it is. And then I need to write that plus, I need to write that as it is, and then differentiate this one, right? That's what went on when I went from this vector and differentiated it to get that vector, and this whole two terms of this vector. Yeah. So this, again, to reiterate, this thing that I wrote over here, that's acceleration of C1 and 0. Yep. And all of these vectors are, of course, expressed in the zeroth frame. So I can go ahead and plug that in the first equation right here. Yeah. And what I get is something like f01x, f01y, 0, plus m1, 0 minus g, 0, because that is that minus g is it y minus, because gravity acts in the negative y naught direction by assumption. Yeah, even though I didn't say it, it is. Gravity is in this direction. Okay. And what else do we have? We have minus f12, which is f12x, f12y, 0. And that minus m1 times the acceleration of c1 and 0. And I just have it right over here, right? So I have all those terms, which is not going to fit into this line, so I'm going to be a bit more clinical. And it's going to look like m1 a1 divided by 2, yeah, times theta 1 double dot cosine 1 sine 1 0 plus theta 1 dot squared minus sine 1 cosine 1 and 0. Everything equals 0. Yeah. Okay, very good. So this is the first equation expressed in coordinates, okay? This is the first equation expressed in the x0, y0, z0 coordinates. What about the second equation, this one? If you want to express that in the zeroth frame, of course, I need to find these cross products, and we did that in class today, or on Tuesday at least, because I'm shooting this video after midnight. So I just wrote the vector that goes from O to C1. So the vector that goes from C to O, C1 to O, right, is just a negative of that vector. So I need to go ahead and compute some stuff here. So let me do that. So what do I need to compute? I need to compute our C1O cross F01. And this one is pretty much, looks like this, minus A1 over 2 sine 1 minus cosine 1, 0 cross F01 is F01x, F01y, and 0, yeah? So if you do this cross product, what do you get? Well, what you get is minus A1 over 2, 0, 0. It's going to be sine 1 F01y and plus cosine 1 F01x. Yeah, that's what you get. If I look at this term right here, this one, yeah, this is C1 to A. The position vector from C1 to A cross F1 to. Well, the position vector from C1 to A is exactly the same thing as position vector from O to C1. Yeah? And the position vector from O to C1 is exactly the negative of position vector from C1 to O. So this is pretty much equal to this term I'm writing right now. Our position vector from C1 to A cross F12 is equal to exactly this, but just replace F01y and F01x by F12y and F12x respectively, yeah? So it looks like minus A1 over 2, 0, 0, sine 1 F12y plus cosine 1 F12x, yeah? There you go. Okay. And so now I'm in a position to write this whole thing down, the second equation down, which reads this guy minus that guy, yeah, let's see, just a second. Our C1A is equal to, so just I forgot. Our C1A is exactly equal to minus our C1O, which is equal to our O to C1, and our O to C1, they don't have the minus, so I don't have the minus here. Okay. 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 So far, so good. Next up, we just write that second equation, which read something like this one first, plus C1 F1x, and then a minus this one, which now reads A1 over 2, 0, 0, S1 F1 2y, plus cosine 1 F1 2x. Next, I have my torque in the z0 direction, so this is going to be plus 0, 0, tau 1. And then finally, the inertial torque, which reads minus 0, 0, the scalar I1 times the angular acceleration, which is what? Theta 1 double dot. This is in the z0 direction, you see. Yeah? And all this thing equals 0. And this here is the second equation in coordinates. So far we've gone through in class. Let me finish this video here, and in the next video I'm going to continue with the third and the fourth equations, how to write them in the coordinates, and then put everything, collect everything in a vector, matrix vector product, and I'm going to form this ax equals b equation, whose solution will give me all the unknowns. Okay, see you in the next video.